Okay, good afternoon. And let's say this talk is for showing the relevant capabilities, relevant features that have been implemented in TerraFlow for the optical control. This is the outline of this presentation. So we will have a general discussion on the components and the interaction in the TerraFlow architecture. Then we will see some operational details of what are the relevant phases that we implemented for the control of optical networks. And I will provide you some, let's say, experimental results or experimental hints for two main POCs that we target in different European projects. And finally, we will do the conclusion with possibility to collaboration on further improvements of this component. So I think you already have seen more or less this architecture with the different blocks. What we did is to create a new block here, that is this optical controller, that was, let's say, integrated with the rest of the architecture that you can see there. In particular, what we did, this is just to highlight the relevant parts that are important in the context of the wide TerraFlow architecture. We were collecting, we extended somehow the MBI to contact the service for the activation of an optical service. This service block was interacting with this optical controller in order to perform some traditional operation, finding a path, computing the spectrum to be used for this connectivity. Finally, the southbound interface of the drivers present in TerraFlow have been integrated with new elements for configuring the optical devices that we will encounter in our system. Of course, consider that the case of using the MBI of TerraFlow opens the possibility, and is a traditional way of interacting with TerraFlow, opens the possibility to have a sort of hierarchical control with a more comprehensive ecosystem interacting maybe with packet and optical domains. More in deep, what's inside this optical block? This is a Python-based component that has been ad hoc designed for TerraFlow. It is, let's say, implemented in two main blocks, functional blocks. The first one that is the part of the API, that at the moment is based on REST, but it will be then moved to gRPC. And then there is another element that is called routing and spectrum assignment, more traditional one, that is the one that performs all the computation for the optical system. Just for you to know, because maybe can be useful for further developing operation and activities in TerraFlow for the optical part. This is the list, more or less, of the APIs that are there available, where we can convey the creation of a flex LiPath, a normal LiPath. We can delete the LiPath, we can create optical bands, we can retrieve information from the optical controller. How it works, these components, so consider if we have an optical network, this is a very simplified schema with multi-band operation. What this module does is to perform a path computation. So at the moment it does a computation with a Dijkstra algorithm for computing a shortest path among the nodes of interest. Then it retrieves all the availability of the slots for the optical spectrum available in each traversed link. As you can see, we have different IDs for the C-band, L-band, S-band. So it performs an integration of those metrics to find the spectral contiguity among the continuity along the path. And finally, according to policies, at the moment only the first fit is implemented, the following with a sort of priority: C-band first, L-band as second option, and last option is the S-band, the selection of the slots to be used in the system. In this case, for example, the path that has been selected is from T11, that is a transponder, then we traverse RODM1, RODM2 to arrive to the other transponder on the other side, with the slot selected 5, 6, 7, and 8 according to the availability in the links that are traversed by the system. For example, as an example, I put here that the middle link does not include all the slots, but we start with the first fit policy to select the first slots available to deploy the optical connection. Finally, this optical slot availability is updated in order to keep in consideration that this slot has been deployed. The optical controller provides a reply that at the moment is based on a JSON. What's inside this reply? We have some information about the requested parameters. So source endpoint, destination endpoint, the requested bitrate, if the connectivity is bidirectional or unidirectional. Then we have information about the spectrum that has been reserved for this connectivity. Finally, we have a portion that we use for a sort of flow entries, flows that have been derived, informing input and output for each node that is present in the system. And finally, we have some information about the band and the operational board and the path details like a list of links and a list of nodes, middle nodes that are traversed. All this information is passed to the service that will be able to perform an allocation of tasks according to the structure of TerraFlow in general, for then communicating with the southbound interfaces. In the southbound interfaces, few drivers have been added. In particular, we were following the traditional approach of netconf and Young modeling for the control of the optical nodes in order to perform the configuration from remote of those devices. Of course, the driver will prepare an XML that is sent through a netconf over SSH channel to the device to ask for the configuration, doing an edit config. In particular, three main drivers have been developed. An OpenConfig terminal devices that we used for the configuration of transponder, muxponder, and IP over WDM devices. An OpenConfig wavelength router that we used for middle node where we do the optical cross connection, in particular for a configurable add and drop multiplexer, the RODMs. And finally, we recently added also an OpenRODM driver, it's very preliminary, to perform the configuration of the RODMs, but according to the OpenRODM Young structure, so that we can have both OpenConfig and OpenRODM devices controlled in the same optical domain. And TerraFlow will perform the proper configuration according to the type of the nodes. This concludes the general overview. Let's move to the operational details. As you can see, we start with how to discover the topology. So in TerraFlow, now I think you start some practice on how to interact with TerraFlow. You have JSON files for retrieving the topology. This works in the same way here in the system, but the fact is that for the optical devices, we implemented a dynamic discovery of the endpoints. So the endpoints are not included within the JSON file that includes devices, for example, or links, but those elements are dynamically retrieved from the optical nodes once the first time the driver connects the agent by doing a get RPC. So the reply of this remote procedure call is passed, and for example, the relevant elements of the hierarchy are retrieved according to the different modeling. For example, we get ports, we get interfaces, we get channels, and in this way, the device can be automatically performed. At the moment, there is only one moment this function invoked, that is the first configuration. Maybe in the future, this can be triggered even to maybe if we extend the device with additional ports or something else to discover new elements. How to push the configuration of a topology? Of course, what we did is to try to keep as much as possible the backward compatibility with the main Teraflow infrastructure. And in particular, for the devices, what we did is exactly use the same JSON structure that it was present in the past in Teraflow without doing any change. No changes other than, of course, pointing to the right driver. For example, 11 is the OpenConfig driver in the system, and including, of course, the entry points of IP address and port for connecting this remote device. And so you can have a list of nodes included in the JSON that include this structure. As you can see, there is no endpoint list. In this case, this endpoint list will be automatically computed by the driver after the first connection to the node and populated with all the relevant information. I will show you in next an example with all the three drivers. Then what about the links? We have the same structure that we have in the system, but we added a portion for including the relevant information that were needed by the optical controller to perform the configuration. Because at the moment, let's say the optical controller is using the context topology for doing the path computation and is updating the context topology after the activation of each system. So it does not have separate database, so everything is included in the main context database of Teraflow. And in this case, we extended the structure of the links with maybe some information, the length of the link, because this can be very crucial for time sensitive or for deriving the latest information, ports information, and the slots availability that you can see in all the slots. What happens is that once we discover the device, it retrieves all the information on the relevant components that are needed in this case for populating the device. For the transponders, according to the OpenConfig terminal device model, we are pointing to the optical channel components, and in this case is the output of a device that was including 4 line interfaces, so 4 channels in the system. For the wavelength router, so the RODMS device, the ports are discovered, and in particular we were discovering the name of the port and the type of the port. Of course, an endpoint UID is assigned to each of them. For the OpenRODM, same history, so we get all the interfaces, highlighting the name, the type, and eventually the location, because this is a modular structure. Regarding the view that you can have at the end of the procedure after the discovery of the topology, if everything works with the devices and the links that you populate, you will see a list of links that appear like this. So a list of elements that can be explored in order to see details and slot availabilities and so on. Regarding the service part, so let's move, this is the topology discovery. Regarding the service part, we use the same technique in the sense that we use this JSON part, the JSON descriptor, for the deployment to MBI or to the REST API, the web UI of the system for the deployment of a service. In this case, a new type of service has been defined, that is this service type optical connectivity, that is valid for all the possible services, types of services that we implemented in the system. Of course, in this request, we provide the endpoints. So I want an optical connectivity from this node to the other node, and we can provide the service constraints, those are used by the routing and spectrum assignment slot for performing some computation and the selection of the slots of the paths according to the different KPI. What are the service constraints that we can use? We have, for example, the type that can be flexigrid or multigranular. I will explain what is this. The possibility to select the bit rate that we want for this optical connectivity, or 800 gigabit per second, 400 gigabit per second, 100 gigabit per second. This is used to map this bitrate to an operational mode. If we want a bidirectional or unidirectional connectivity, and finally, if we provide this multigranular approach, the portion of the spectrum that we want to reserve for the connectivity. This is an example of JSON that we used, where we have the service type, the end source and destination endpoints, and the constraints. This is the case for a FlexiGrid activation. Of course, we have developed a web page in the web UI devoted for the optical connectivity, where we can retrieve all the relevant details for our system. And so we can further investigate the behavior of the things, the resources that have been used for the different system. Let's move now to the usage of those, let's say, conceptual information and designed the components that I just described. I would like to highlight that these activities have been performed in the context of two European projects, where we contributed for the optical content of TerraFlow. It's FlexScale, where we were targeting this multigranular and multi-layer optical connectivity, and the season one, where we had this IP over WDM with FlexiGrid and apparent hierarchical control. In IP over WDM FlexiGrid environment is, let's say, the traditional environment. The only thing is that maybe we have at the edge not transponder, but IP over WDM. In this case, as you can see, we have exactly a similar setup of a service for this device, where we provide a type FlexiGrid. We are asking for 800 gigabit of bandwidth, and we want a unidirectional connection. This was just an example in the system. Here you can see below that this is more or less the logical representation that we have of the TerraFlow architecture, where we have the 3 rodents and the 2 IP over WDM boxes at the end, with a LiPAT that will be instantiated in the system. So after doing the path computation, routing and spectrum assignment as described before, a set of XML are prepared by the sound-bound interfaces in order to configure all the devices. In particular, this is the example of a configuration that has been performed for the IP over WDM with 800 gigabit per second. So we select a frequency among the ones that are available. The first fit, in this case, this was the first frequency that was available in the C-band. Then we set the target output power of the transceiver to 0 dBm, and then we put this operational mode 8. This operational mode 8 is the one that maps the bitrate that was requested in the connectivity. What happens for the middle node? Of course, the driver, in this case the OpenConfig for wavelength router devices, will perform the configuration of the traversed rodents in the system, providing the information about the portion of the spectrum. So in this case, we are allocating 100 gigabit per second for this connection in order to serve 800 gigabit per second. And we perform the information about the ports, input and output port that has to be configured for the system. And so in this case, this message is serialized. 3 tasks are created for performing the configuration of the traversed devices. And after this, the LiPAT becomes active in the system. This was the FlexiGrid environment. Let's move to the multigranular node. So with the multigranular node, sorry, there is a problem in the visualization here. We have this, let's say, network that is based on innovative optical nodes that are capable of switching at different granularity, fiber, large portion of the spectrum, or LiPAT, so in the traditional way. In this case, we are using this multi-layer approach, so that we do first the switching of a wide portion of the spectrum among multigranular optical nodes, and then we append media channel on top of this big pipe that is instantiated in the system. So in this case, the behavior of the system is completely different. It operates in two steps. First, we have to create the optical band, and then we have to create the media channel on top of it. And in this case, for example, you can see the parameter that we send. So we have a system, a service that is multigranular, with the connectivity 800 gigabit per second. So this is the connectivity at the transponder. We want a unidirectional one, and we are asking for the allocation of a wide band of 600 gigahertz in the spectrum. And then once the waveband is created, the media channel are appended to this system. Let's see how what's the driver send in this case. I didn't replicate for the lack of space in the slide the configuration of the transponder. Consider that is exactly the same modeling that we applied in this case. But for example, this is the configuration that we send for configuring these multigranular optical nodes. As you can see, we have this optical bands part that have been extended in the traditional wavelength router model for conveying this big pipe. At the end of the procedure, after configuring all the traversed node, the waveband becomes active in these devices that are traversed. Then, on top of this, the configuration of the media channel is sent. And so the final setup is performed end-to-end. In case, for example, we want to perform the configuration of another transponder exploiting the waveband, we will not need to reconfigure the waveband. This is already there. We just need the configuration on the multigranular optical node 1 and 3 for appending the new media channel to the system. Okay, so we are at the end of this talk. I tried to fit in the time that has been given to me. So we have seen the key information, the key functionalities of this optical TerraFlow instance for controlling heterogeneous devices, including OpenConfig transponder, terminal device, OpenConfig wavelength router, and OpenRODM. We have described the operation for the topology discovery, for the service deployment, and of course we have validated the proper behavior of the southbound drivers for the system. There is already something that is on the chain, that is the support of this point-to-multipoint system. This is the scope of another European project where we are involved together with CTTC, so that we can extend the capability of TerraFlow supporting even this point-to-multipoint part. We know that there are existing limitations. So this is let's say, the first time that we describe so in detail the optical capabilities of TerraFlow. Well, at the moment, this is running a simple Dijkstra algorithm, so without considering k-shortest path or more advanced path computation. So it's something simple. Of course, there is some limitation in the single edge topology, so we cannot have in current modeling in the optical controller more than one edge in the same node. We know about these. We would like to work to solve this issue. And of course, at the moment, there is this REST API that was very good for the development part, where there are changes that occur very frequently in the system. Now, I think with that the things are more or less stable. We can move towards the gRPC protobuf modeling for those APIs, keeping the same functionalities, but integrating in a cloud native way with the rest of the architecture. Of course, we are going to integrate the monitoring capabilities of these. It's the last part of one of the projects that we are encountering, implement retrieving telemetry from the devices and perform closed loop operation in the system. And so even doing some zero-touch service reconfiguration in case of special events in the system. Of course, we are also caring about the overall interfacing of Teraflow towards the rest of the world by providing an alternative to the Teraflow northbound interface that is a custom one to use a more standard API supporting, for example, transport API modeling for this purpose. So this concludes the talk, and now I'm open, available for question, comments from you guys, from the audience.
Thank you very much, Andrea.
Yeah, okay.
Yeah, please go ahead with the. No.
Sorry.
I just wanted to thank Andrea before asking for the questions. Please go ahead.
I have two questions at least. Andrea, can you please go to slide 7 first?
Yes, of course.
I think it's better to go there. Okay, just to be clarified at some point. So here you mentioned you have 3 main SPR modules: OpenConfig, OpenRODOM. So just to clarify, so let's say if some company or for some devices does not have full support for OpenConfig or OpenRODOM, let's say if they only have netconf support. So does it mean if they provide you simply the young module, then we can simply use netconf to do everything?
Let's say in this case, so this is a good point. In my opinion, in this case, if you have a different young modeling, what you can do is that maybe we can create in Teraflow a new driver in the system that maybe will be the vendor A driver for controlling through netconf the devices. And of course, this should work so that maybe we can have some testing session to understand what are the relevant information first to discovery at the first connection, and then to configure if you want to perform some configuration, and that's it. So that the behavior of the system is what we did. So we did the logic on the top, and then you can just modify the drivers in order to perform some special operation in the device. Yes, of course.
So that means we may need to make some write some script to make some map or some translator, or no?
This is up to you, in the sense that the best way that I see is to deploy a new driver, to activate a new driver that can perform this information. Otherwise, you have to do something, let's say, in the middle, so that receives maybe OpenConfig and adapts to your things. But at this point, you will be not, in my opinion, Teraflow compliant. So it would be nice to have, let's say, in case you need, we can maybe provide support on this purpose, for this purpose. Yes.
Okay, thank you. So second question is, you mentioned about IP over WDM. So yes. You have used some plugboards, I assume, yeah?
Yes. Yes.
So the plugboards, let's say the plugboard from, let's say, if from the router company like Cisco or Juniper, how is it easier, or how is it controlled or configured?
This is a good point. It's a good and huge point, I would say, because for our validation, what we used is a Sonic-based environment where I developed a netconf agent exposing OpenConfig and communicating through CLI or through CNIT to the driver for the configuration of the pluggable. We had ZR and ZR Plus 400G QSFP-DD pluggables for this configuration, and we were able to perform the configuration of the pluggable, setting the frequency, doing all the activating the pluggables in general from the netconf agent from the Teraflow elements. Yes. So for the Cisco devices, I don't know whether the Cisco devices, I read that they support OpenConfig. I saw there is a page on the web, that is this support of ZR pluggable in Cisco devices that is following OpenConfig approach, where they explain how they adapted the terminal device modeling for the configuration of the device. So it depends. Strongly depends on if there is netconf capability in the routers, which modeling they use. If they use OpenConfig, traditional, let's say, proper OpenConfig device, the modeling, this should be straightforward for the configuration of the device. Yeah.
Okay, thank you very much.
You're welcome.
I have another small question. So generally, in our controller, we have our own controller, of course. We have the node, we have chef and the slot. So here, you seem you don't use chef, this number, correct? So let's say if you want to differentiate the slots in one chef from another chef, maybe we can simply add the chef number to the slot, maybe together like 1.1 or 2.1.
Yes. Let's say that this was a very simple logic where let's say we did a sort of simple mapping among port number and let's say name of the optical channel. In another activity, we did this complete end-to-end mapping, including shelf ID, card slot position. We did the card for the slot with a clear mapping among position in the device and the name of the objects in order to be working and complete end-to-end in the overall system. Yeah.
Yeah, okay. Great. Thank you very much.
You're welcome. I don't know if there are other questions.
More questions for Andrea?
I have one. So you mentioned at the very end Transport API as a northbound interface. Would you also see that as a southbound interface instead of OpenConfig? And I mean, because we are working on a challenge that is trying to get the topology from TAPI, and I think that's from the southbound interface.
Exactly. Exactly. So at the moment, let's say I moved to this representation because it's, let's say, can you see still my screen, correct, guys? Okay. So it's a way that we can use Transport API. So now I think you are using in the southbound, so as let's say a south interface to communicate with some entity that is below your Teraflow instance. This let's say TAPI driver, TAPI plugin for retrieving the topology from another element. So the server TAPI, it's running on another part that is the one that expose the topology, that is the one that expose API for performing a configuration of a service. So we would like to, let's say, extend this, let's say, this MBI, instead of using the Teraflow custom, let's say, API, that is a REST-based interface, but with a modeling, with a structure of the messages that is based on Teraflow, that has been developed within Teraflow, to change this to be a TAPI compliant one, so that it will be standard with clear parameters to be sent for performing some configuration, or clear modeling when you export a topology to the other device. Okay, so to the top. So in this case, we are talking about the other side. So the top level of the controller is more on the node-bound interface. Of course, consider that the modeling in those systems is the same, so that in one case you have to query something and pass the reply. In the other case, you have to expose objects according to a specific modeling.
Yeah, okay. Thank you.
You're welcome.
More questions from Ricard? I see he has the hand rising.
I cannot see the people, so
no worries. I have the screen.
It was a follow-up. It was a follow-up. Maybe I don't know if it's for Andrea or for you, Luis. But I remember we were working on TFS MBI it's called TFS API, and I don't know the status. I see it has been touched quite recently, so maybe there is still some work being done on what Andrea was mentioning. Although the question was for the southbound, clearly for the end-to-end orchestrator, I think that we expose this the TFS TAPI interface, no? Or no?
The TAPI on the northbound, it's not exposed.
Okay.
It's an open discussion that we have, let's say, ongoing work with Andrea.
Yes.
Okay.
We started something. Okay, let's say in this way, so that we have some skeleton. There is a guy, a colleague of mine, that is working on this topic. So, yeah.
Have you tried maybe to use an LLM for that?
No,
because
I hope
I have seen
the guy
nice,
didn't.
I have seen no, because I have seen nice results from LLMs that automatically translate models.
Okay.
So it should be quick to go from Transport API to TFS API.
Yes.
It should not be something complex.
Yeah.
It works.
I'm quite sure that this is the case, because the only thing is that then you have to map the JSON, the JSON structure in order to include the fields and the things that you need on the other case. Maybe just having a couple of examples, this would be nice. So let's say you have this code that is the MBI that we have on one side. This is, let's say, the modeling. I want to have this other modeling for the same topology. Can you prepare the code for me? And maybe you don't know what will be the output of this.
I have seen a paper from, I don't know if it is published or not, but a paper that did the translations of several young models, and the evaluation was quite good. With some guide rails, it performed very well.
Okay.
So
it can be a good advice. Thanks, Ricard, because maybe we can. I have to check what's the status of this implementation, because maybe now it's in a good shape. Let's say the guy was already retrieving the topology. So let's say serving a topology. And so maybe we have something already, but
you have almost 2/3 of the job done. If you are able to retrieve a topology, you have almost everything. Because, then you need to do the service mapping, and it's just a follow-up. Yeah. Okay, thank you.
Okay, you're welcome. Thank you, Ricard, for the first comment. Okay.
More questions for Andrea? Okay, seems not. Then thank you very much, Andrea, for joining and the very nice tutorial on